Hi everyone. In this video, we're going to talk about the ratio test. The ratio test is the test we can use to determine if a series absolutely converges. And here's how it works. Suppose we have a series sum of an, and let L be the limit of the absolute value of an plus 1 over an as n goes to infinity. Then we have three cases. If L is less than 1, then we have that the series converges absolutely. If L is greater than 1, or goes off to infinity, then the series diverges. And if L is equal to 1, then the ratio test is inconclusive, and so we have to use another test. A quick remark before we move on to some examples is that the ratio test is especially useful for series that involve factorials or n's and exponents. And we'll see why that's the case as we work through these examples. Consider the series sum from n equals 1 to infinity of minus 1 to the n minus 1 times 2 to the n over n factorial. We compute the limit of the absolute value of an plus 1 over an, and because of the absolute value, we can get rid of the minus 1s. Then, we rewrite the quotient of fractions as a product of fractions by taking the reciprocal of the bottom. Once we have a product of fractions, oftentimes it's helpful to group the terms that we have by type. What I mean by that in this case is grouping the exponential terms to get 2 to the n plus 1 over 2 to the n, and grouping the factorial terms to get n factorial over n plus 1 factorial. And now we see that quite a bit cancels. In the fraction with the exponentials, we have n plus 1 factors of 2 on top and n factors of 2 on the bottom. So all but one of them cancel, and we're just left with 2. And in the fraction with the factorials, we have n factorial on top, which is 1 times 2 times 3 all the way up until n. And on the bottom, we have n plus 1 factorial, which is 1 times 2 times 3 all the way up until n plus 1. So the only difference between the top and the bottom is that the bottom has an extra factor of n plus 1. Therefore, everything else cancels, and we are left with 1 over n plus 1. Finally, we can take a limit and find that this goes to 0, which is less than 1. And so, by the ratio test, our series is absolutely convergent. Next, let's think about the sum from n equals 1 to infinity of n to the n over n factorial. We start off exactly the same way, computing the limit of the absolute value of an plus 1 over an. And then we can turn the quotient into a product by reciprocating and group the terms that look alike. Just like in the last example, we can cancel the factorials to get 1 over n plus 1, and now we see that one of the n plus 1s on top cancels with the n plus 1 on the bottom. And so we're left with n plus 1 to the n over n to the n. Since both are raised to the n power, we can pull out the power of n and get n plus 1 over n all to the n. Dividing out by the n in the denominator, we get 1 plus 1 over n all to the nth power. Now, this limit isn't immediately obvious. However, if you recall, when we talked about the exponential function, we showed that this limit is actually equal to e, which is a number bigger than 1. Therefore, the series diverges by the ratio test. Let's go ahead and do a couple more examples. First, consider the sum from n equals 1 to infinity of minus 1 to the n times n over 5 to the n. Again, we start by taking the limit. We can get rid of the minus 1s because of the absolute values, rewrite the quotient as a product, and group like terms, and cancel the 5s. Then we see that the limit of n plus 1 over n is equal to 1, and so we get out 1/5, which is less than 1, and so the series converges absolutely by the ratio test. And finally, let's try to decide whether the series sum from n equals 1 to infinity of minus 1 to the n over n squared converges or diverges. Just like we always do, we compute the limit. And after we simplify, we are left with the limit of n squared over n plus 1 squared, which turns out goes to 1. Therefore, the ratio test is inconclusive, and so we'll need to use another test to tell if this series converges or diverges. However, going through our toolbox, we see that the series converges by the alternating series test.